Hello again. In this set of slides, I want to take a look at two different topics in wave optics, diffraction gratings and single slit diffraction. So we're going to start with diffraction gratings. What is a diffraction grating? We had earlier taken a look at the situation of double slit interference when a coherent plane wave of light simultaneously strikes two slits. We get the famous Young's double slit experiment, which demonstrated that light is a wave-like object. But what happens if we increase the number of slits? So 2, 3, 4, 5, 6, 7, however high we want to go, an arbitrarily large number of slits through which we have these coherent plane waves of light passing. And each little slit is going to serve as a source of light. What happens? Well, it's basically interference on steroids. We are going to have lots and lots of all of these parallel rays together, and all of them have to combine to create constructive interference, or we need to get cancellation between all possible pairs to get destructive interference. And that sounds complicated. Fortunately, the formula isn't too bad, because the formula relies on an idea that we've seen before, path length difference. And the path length difference, if we are at some angle theta, is once again, just like with the double slit experiment, it's going to go as d sine theta. This is going to make the diffraction grating situation deceptively like the double slit situation. We are going to see that d sine theta is equal to m lambda. That's exactly the equation that we saw with double slit interference. Be careful. If faced with a problem, check to see whether it's two slits or a diffraction grating. There is a difference that we're going to discuss. The actual angle in the diffraction grating situation is actually not necessarily small. In the double slit interference case, we can say theta is a tiny amount. That's not necessarily the case in the diffraction grating. Now let's try and build up a little bit to an understanding. In the two-slit situation, we get this set of spots that more or less have even intensity. Just to make sure that you are understanding this plot correctly, the right side of the figure is where the screen is. And as the peak moves out to the left, that represents the location of a bright spot on this vertical screen. So in the double slit experiment, we have a series of evenly spaced, roughly equally bright spots. And they're very close together. What would happen if we had three slits? Well, you can see the pattern that you would wind up getting. You would get these major spots, and then in between the major spots, you would get these very minor spots, much less bright than the major spots. And what would happen if we went to four slits? Well, you still see these bright spots, and now you see two separate weak spots. And what's happening is these weak spots are actually a little bit dimmer than the weak spot in the three-slit interference. Take a look at how large this tiny peak is in the three-slit interference case, and then compare it with the two different peaks in the four-slit interference case, and you'll see that the peaks have decreased, indicating that they're even less bright. Let's go to five slits, and what we have is an even dimmer set of spots in between the major spots. And if we extrapolate this outwards, the major spots retain their intensity, but the little spots in between basically fade out to zero. And the pattern that you wind up getting in the diffraction grating, where you have a huge number of slits, way beyond just 5, is that you get these bright spots, that are actually relatively widely separated from each other. They are not going to be within a tiny angular range like the double slit case. These values of theta are going to be significant, and the small angle approximations will not apply. So the peaks are getting narrower and narrower to indicate that the bright spots are getting more and more focused, but they are also getting more widely separated. What we would see in a diffraction grating intensity pattern are these intense bright spots that are evenly or close to evenly spaced from each other. And unlike the drawing for the double slit experiment in the previous lecture, this is not entirely wrong in its scale of the actual angle at which the spots occur. So yes, you would get a real, a significant spot, a bright spot out at 30 degrees, 40 degrees, etc. That does happen with a diffraction grating. Theta is significant. We can otherwise still use much of the same terminology as we did with double slit interference. The central spot is n equals 0. The first spot on one side is m equals 1. The second spot is m equals 2, so on and so forth. So that part is the same. Much of what we see in d sine theta equals m lambda is the same, but theta is not small. So we just get the same equation as before, but with that difference. Let's take a look at this example on the screen. We have a diffraction grating, and it's described as having 1,500 lines per centimeter. And the pattern is projected onto a screen that's 2.53 meters away, and we're told that the n equals 1 peak is at 35.5 centimeters away from the n equals 0 peak, presumably measured along the screen. And the question is, what is the wavelength of the light? And then a follow-up question, how many peaks could we see if our screen were wide enough? Because if we project this pattern onto the screen, we will get a central bright spot at theta equals 0. We'll get an n equals 1 spot, that's some significant angle away. But we'd get an n equals 2, that's further away. N equals 3, that's further away. N equals 4, that's even further away. What's the maximum value of m? It is a finite number, as we'll see. But one thing at a time. What does this 1,500 lines per centimeter mean? It's equivalent to stating that there are 1,500 slits in just a single centimeter. These slits are extremely finely separated from each other. I want to do this in standard units. If there are 1,500 slits per centimeter, then that would mean that there are 150,000 slits per meter, or 150,000 lines per meter. And we get our separation D, the separation between the slits, as 1 over the number of lines per meter. So D is equal to 1 over 150,000. D is 6.667 times 10 to the negative 6 meters. So it is extremely small, but it is on a scale that is comparable to what a light ray's wavelength is. For the n equals 1 peak, we can consider a right triangle. The slits, the diffraction grating is 2.53 meters from the screen. The central spot would be right along the end of the horizontal line, and the n equals 1 spot is 0.355 meters above it. So we can find theta 1 using some trigonometry. Tangent of theta equals opposite over adjacent. We know what opposite is. We know what adjacent is. We can do inverse tangent on that fraction, and we get 7.99 degrees. Now that we know d, we know m, and we know theta, we can finally solve for the wavelength lambda. The wavelength lambda is equal to d sine theta over m. We know d, we know theta, we know m, we plug it in, we get a wavelength of 926 nanometers. And that answers the first question. But the second question, let's just recall that. How many peaks would we be able to see if our screen were wide enough? As n gets larger, theta gets larger. But theta cannot get any larger than 90 degrees. So what we want to do is we want to find the value of m that gives us the largest possible value for theta that is no more than 90 degrees. So we can do that by plugging in theta equals 90 degrees and calculating what n would have to be. So if we are at the maximum possible value of theta, then we are conceivably at the maximum possible value of m. If we set theta max equal to 90 degrees, the sine of 90 is 1, and what we find is that n max is less than or equal to d over lambda. We know d, we just found lambda, we get that the maximum possible value of n is 7.2, but n has to be an integer. N cannot be more than 7.2. Well, the integer that is largest but not greater than 7.2 is, of course, 7. And just as a side note, I'm not rounding up. I am always truncating. If I had found n max equal to 7.9999999, n max would actually be 7. Now that we know n max, we can find the total number of spots. N max is the number of spots to the left of the central spot, and it's also the number of spots to the right of the central spot. So we have m to the left, we have m to the right, plus the central spot itself. We have 2m max plus 1 total spots. There would be a pattern of just 15 spots spanning the entire range. So unlike double slit interference, there is definitely a countably finite number of spots that you're going to see. A fun little conceptual question. We have a diffraction grating that is illuminated with yellow light. The yellow light, of course, is coming straight into it at normal incidence, as it says. And the resulting diffraction pattern has a yellow spot at the center, and then one yellow spot at 45 degrees to the left, and another yellow spot at 45 degrees to the right. Now, let's mix in red light with that yellow light. And we'll assume the red light has equal intensity, so it won't swamp out the yellow, nor will the yellow swamp out the red. And we pass that red light through the diffraction grating mixed with the yellow light. What would the new pattern look like? And you can see the different options. Red spots at 0 and plus or minus 45, or yellow spots at 0 and plus or minus 45, orange at 0 and plus or minus 45, or an orange spot at 0 and yellow spots at plus or minus 45 and red spots slightly farther out, or an orange spot at 0, yellow spots at plus or minus 45 and red spots slightly closer in. Now I'll give you a little bit of a hint to answer this question. Yellow light and red light do not have the same wavelength. They do not have the same values of lambda. Determine which of those colors has the larger value of lambda. And then consider what happens. D sine theta equals n lambda. Both of them are going through the same diffraction grating, so both of them are experiencing the same D. But if lambda goes up, what happens to theta? And that should tell you the answer for what you're looking for. Okay, let's move on to single slit diffraction. So we've looked at 2 slits, 3 slits, 4, 5, an arbitrarily large number of slits. We have yet to look at 1. We have yet to look at what happens when light passes through a single slit. And this is surprisingly more complicated than you might think. If you already think that this stuff is kind of complicated, single slit diffraction, the explanation behind it is a little bizarre. Why is it a little bizarre? Because we have Huygens' principle coming into play for this explanation. Recall that Huygens' principle says that any single individual point in a wavefront effectively serves as a source of waves itself, a source of waves of exactly the same wavelength. So as the light passes through this single slit, each single point, each single geometric point along this vertical red line, this wavefront of the incoming wave, is serving as a source of spherical waves. It would look something like this. Each individual point serving as a source of spherical waves. The net effect would be essentially this wave function right here. We would see that for much of its length, the wave function is parallel to what we saw earlier, but we also see some curving around on the edges. But that's not the entire story. This is where it gets a little weird, because these individual sources are acting as sources of light, are interfering with each other. As crazy as this might sound, this is what is happening. So consider a source at the very top, right where it hooks up to the edge of the slit, and then another source right in about the center. And then we're just going to look at these possible pairs and their interference with each other. And I can imagine this pair, and this pair, and this pair, this, all possible pairs with one in the upper half and the other in the lower half, interfering with each other. The path length difference turns out to be 1/2 times A times the sine of theta, and we get destructive interference between them if this path length difference is equivalent to half a wavelength. Or if I want to get rid of these factors of 1/2, I would say that A, which is the size of the slit times the sine of theta 1 equals 1 times lambda. But it doesn't stop there. I can also divide my slit up into 4 segments, and I can look at interactions between possible pairs there. So now we have these different interfering sources, and the path length difference between these pair of sources, like the pair in the upper half and the pair in the lower half, is A over 4 sine theta. And if A over 4 sine theta is equal to 1/2 lambda, if the path length difference is equal to 1/2 lambda, we get destructive interference. Well, correspondingly, the condition is A sine theta equals 2 lambda. So we've divided it by 2, the slit width by 2, and we've divided the slit width by 4. Can we divide it by 3? And the answer is no. If I divide it by 3 and then I try and look at interference between pairs, I can look at interference between a source in the top third and a source in the middle third, but then I would have to look at a source between the middle third and a source in the bottom third, and the sources in the middle third get used twice, and that's not legitimate. So I don't see any contribution from the situation where I divide the source into an odd number of regions. It only works when I divide the source into an even number of regions. And each time we divide it into an even number of regions, like we saw with our 2 slits and our 4 slits, we get, in the case of dividing it into 2 halves, we get A sine theta equals 1 lambda. In the case of dividing it into 4 halves, we get A sine theta equals 2 lambda. If we had 4 halves, 4 quarters. If we divide it into 6 equal regions, we would get A over 6 sine theta equals 1/2 lambda, or A sine theta equals 3 lambda. Or we could do A sine theta equals 4 lambda, or 5 lambda, or 6 lambda. So we get this pattern of A sine theta equals M lambda for our expression for single-slit diffraction. Bear in mind, we are strictly looking at destructive interference. We could look at constructive interference, but there is a rather different thing happening in single-slit diffraction that does not happen in multiple-slit diffraction. The big difference that we have in single-slit diffraction is that the light tends to fall into a central blob. There is a broad, bright spot at the very center of the single-slit diffraction pattern. And then there are lesser spots trailing off to one side or the other side. In the equation for single-slit diffraction, we are not looking for the bright spots. We're looking for the dark spots. So theta is still measured with respect to the very center of the pattern, the very center of that bright spot. But we are measuring theta out from that center of that very bright spot to a dark spot. Like we see in this very rough drawing here, we see that central bright spot. It has a relatively large intensity and it's relatively broad compared to the others. And we see that the different angles are subtended from the center of the bright spot to where the intensity is zero, where we would have a dark spot. So that's what theta represents in single-slit diffraction. That makes it different from the other multiple-slit diffractions that we've been examining. In the double-slit situation and in the diffraction grading, we use the expression d sine theta equals m lambda, and that gets us the bright spots. In single-slit diffraction, we say a sine theta equals m lambda, and that gets us to the dark spots specifically. Make sure you know what you are examining when you do these problems. Let's do an example. We have light with a wavelength of 558 nanometers incident on a narrow slit. We project this onto a screen that's 179 centimeters away. And we measure the bright spot to be only 9.14 millimeters wide. And the question is, what is the width of the slit? Now, the one thing that single-slit diffraction has in common with double-slit diffraction is that the angles are small. We can use the small angle approximation in single-slit diffraction just as we did in double-slit diffraction. It's just now we have the expression a sine theta equals lambda, and we're looking for the dark spots. It says the bright spot is measured to be 9.14 millimeters wide. Let's make sure we understand that. So when I say that the bright spot is 9.14 millimeters wide, I mean the length of the spot from the dark spot on its right to the dark spot on its left. I measure that distance, and that would be the width of the central spot. So I'm actually interested in half of that entire length. So I want to take the width of the entire the entire central bright spot, and divide it by 2. And that's going to be the distance from the center of the central bright spot to the dark spot in question. And since we are talking about the dark spot immediately adjacent to the central bright spot, that implies m equals 1. So tangent theta equals opposite over adjacent. We can plug in the numbers, and we get that theta 1, if we want it in degrees, we do have to go through the inverse tangent. It's equal to 0.146 degrees. In turn, we can find the width of the slit from a sine theta equals m lambda. We know what lambda is, and we know that m is 1, and we just found theta. We plug in the numbers, and we get that the central slit has a width of 0.000219 meters, or if this were a test question, the answer would probably be expressed as 0.219 millimeters. So once again, we might say, wow, that's really small, but that's a size scale that's very large for the wavelength of visible light. Another conceptual question, we have violet light with a wavelength of lambda passing through a single slit of width A, and it creates a diffraction pattern. If we take this violet light and replace it by light that has twice the wavelength, and if we want to get exactly the same diffraction pattern with exactly the same width, what would we have to do to the slit width in order to accomplish that? So we start with A sine theta equals n lambda. To maintain the same pattern with exactly the same dimensions, I need to have theta be the same. There's your hint. Think about it. Let me know if you have questions. There is an everyday application of single slit diffraction. You are using it almost certainly every day. And that occurs in vision. Because you have encountered this phenomenon before of looking at an object that's very far away and wondering exactly what it is, but as you get close to the object, you recognize it as being whatever. Take a look at the image on the screen. You see a circle and you see a pair of the letter I, two lowercase i's in the center of that circle. Now, if you move your head far enough away, so if you move away from the screen and look at the image, at some point in time, those two eyes are going to blur together, and you won't be able to recognize that they are two eyes. The question that I want to pose is, what's the farthest away you can be from your screen and recognize those two eyes as two separate objects? This is going to give us an introduction to the idea called the Rayleigh criterion, named after Lord Rayleigh, who, among other things, explained why the sky is blue. But the Rayleigh criterion is the limit at which we can say there are two different things there. If we don't satisfy the Rayleigh criterion, we'd say, well, there's something there, but there's not enough resolution to be able to figure out what it is. What is the Rayleigh criterion? What we saw with single slit diffraction is that rays of light that have to pass through a slit create an image with a large central bright spot, but then smaller spots to the left and the right. The Rayleigh criterion says that if the images created by, say, the left side and the right side of an object are no closer together than having the bright spot of one appear at the first dark spot of the other, then we would be able to distinguish that there are two things there. So you can see in the image on the graph, the situation on the left, there's very little overlap between the central bright spot of one letter I and the central bright spot of the other letter I as created on the retina. But as you move farther away, the angular spread between those two letters I gets smaller, and the patterns for each of those created on your retina get closer together. They start to overlap more and more. But you can see in the middle figure that the peak of one is at the same horizontal location as the first minimum of the other. And this is right at the limit of the Rayleigh criterion. You can say right at this limit that there are two things. If things get closer together than that, if there's more overlap between the two patterns on your retina, you just reach a point where you can say, well, there's something there, but I can't see any substructure to it at all. It just looks like a spot. The equation describing the Rayleigh criterion is A sine theta must be greater than or equal to 1.22 times lambda. Lambda, of course, is the wavelength of the light. A is the diameter of your pupil, and theta is the angular difference between the two things that you're examining. The factor of 1.22 comes from the fact that your pupil is circular. For those of you who are interested, the 1.22 can be determined from what is called a Bessel function. And if you don't know what that is, don't worry about it in this course. Let's apply the Rayleigh criterion to the situation of a penny. A penny is 19.05 millimeters in diameter. They're all fixed to be the same size. We're going to pretend that there are no issues with the atmosphere, like a fog or anything like that, and we're going to assume that you have perfect eyesight. And the question is, how far away can we be from this penny and still say, yeah, I think that's a penny? We're going to assume that the wavelength of light is 550 nanometers and that the diameter of the pupil is 1.50 millimeters. How do we solve this? If I want to be able to say, oh yeah, that's a penny, I have to be able to distinguish the left side from the right side. So I'm going to treat the left side of the penny as one object, and I'm going to treat the right side of the penny as the other object. And I'm going to ask for the angular separation between the left side and the right side. The distance from the observer to the penny is capital L. And again, using some trigonometry, we can say that to a very good approximation. The sine of the angle from one side of the penny to the other side of the penny is equal to the diameter of the penny divided by the length. Rayleigh's criterion, well, that's what we're looking for. That is the angle subtended by the penny. 0.01905 divided by L is equal to the sine of theta. So I'm going to take that and multiply it by A. That gives me A times the sine of theta. A times 0.01905 over L is A sine theta. And that's equal to 1.22 times lambda. Well, I know A, and I know lambda. I want to solve for L, the distance from the coin. And L turns out to be 42.6 meters. Now that's actually a very long distance away, and it would be highly unlikely that you can be, that's 140 feet away from a penny, and be able to say, yes, that's a penny. You'd be able to say that there's something there, but to be that far away and say it's a penny requires absolutely ideal viewing conditions, and you need to have some very solid eyesight. You can't have any visual problems at all. So, anyhow, there it is, applied in real life. Take care. Bye-bye.